So, for partial fraction decomposition, breaking that rational expression down into two smaller rational expressions, we're going to go ahead and kind of follow these steps. First, write the denominator in factored form. So that's simple enough. Once we have it in factored form, we're going to use those factors to break things up. And this looks a lot more complicated than it actually is. So we are going to apply these following rules. For every factor that we have where it's like ax plus b raised to a power where n is greater than or equal to 1, we're going to break it down like this. So let's disregard this for a second and look at one like this. Let's say we had 3x squared minus 5x all over x plus 1 times x plus 2 squared. Well, for this one, if we're breaking this down, we're going to have a denominator that's going to be just x plus 1. We're going to have a denominator that's x plus 2. Even though this one's squared, we're going to have just a plain old x plus 2. And we need to have one that's x plus 2 squared. So that's what this one's basically saying is if we had like a higher degree, we'd have to have one for every degree. Highest degree you're going to see is squared. All right, so it would look like this, and we'd have an a instead of a1, a2, a3, a, b, and c. What happens here is every one of these on the bottom is a linear factor. So on top, it's 1 degree less. This is just going to be a constant on top. If we look at the next part, when we have something a little more complicated, like something that's ax squared plus bx plus c, or just something that's to a degree of 2, instead of having just an a on top, we have to go 1 degree less. So this is a quadratic on bottom. We're going to have a linear expression on top. So it's going to be ax plus b on top instead of just a. But we'll break that down so it looks something like this. And then third step is to multiply both sides by that common denominator, which is just the original denominator that's all factored out. And then we solve for our variables. So you'll see once we kind of get started, it's not as complicated as the steps may make it look to be. Just a lot of algebra for the most part. So let's take a look at number 1. I'm just trying to write this, break it down into two smaller parts, or in this case it comes out to be 2. It could be more than 2. All right, first step, factor that denominator. So our denominator, just the difference of 2 squares. We get x plus 3 times x minus 3. All right, each factor is just to the first power. So what's going to happen when we break this down, we're going to get one rational expression over here with x plus 3 as a denominator, and one rational expression over here with x minus 3 as a denominator. That's all we've got. On top, we're just going to have a constant, because these are linear factors, linear functions down here. We're just going to have a and b. That's it. Now, the next step is to multiply both sides. I love this computer. All right, the next step is to multiply both sides by that denominator right here. So we're going to multiply this side by x plus 3 times x minus 3. And that's just going to cancel all that out. Over here we're multiplying by x plus 3 times x minus 3. We have to distribute that to each one. So we end up with 5x minus 3 equals, when we multiply all of this by the first term, the x plus 3's cancel out, and we're left with a times x minus 3. We multiply this whole thing by the second term, the x minus 3's cancel out, and we're left with b times x plus 3. So we're going to want to go ahead and distribute our constants. So we get ax minus 3a plus bx plus 3b. And now we're going to look at like terms. So if you look, we have 2 terms here that deal with x's, and the other 2 have no x's. Those are actually constants. So these 2 are just constants. So I'm going to rearrange these. Put our x's up front, so we have ax plus bx, and then our constants at the end. Well, what happens here is that these x terms on the right side have to add up to give us the x term on the left side. And the constants on the right side have to add up to give us the constant on the left side. So we're going to take this one step further before we go on to solving. For this first one, when we have the x's, I'm going to take an x out, and we get a plus b. Over here, we could factor a 3 out. It's just kind of coincidence. Usually that's not going to happen. And we don't need to factor out anything from the constant, so I'm going to leave that how it is. But basically how this works is these constants, the negative 3a plus 3b, has to come out to be negative 3. And this a plus b has to equal 5. So what we end up doing to solve for a and b is set up a linear system of equations. So the a plus b has to equal 5, and negative 3a plus 3b has to equal negative 3. So we have two equations. And we can solve those by elimination or substitution. I'm going to go ahead and use elimination. We can multiply the top one. I'm just going to multiply the top by 3 on both sides. So we get 3a plus 3b equals 15. And we can add those two equations together. The a's cancel out. We get 6b equals 12. So b equals 2. So we've got one of our two variables. To figure out what a is, we can just put b in here to that equation. Right? So a plus 2 equals 5. So a has to equal 3. But our final answer is not just going to be a and b. Our final answer needs to be this expression right here, but with a and b replaced by these two values. So our final answer for this one is going to be 3 over x plus 3 plus 2 over x minus 3. Right, we can go back and make common denominators for these two, add them, and we would get what we started with. And remember, the whole idea for this is we can't do the antiderivative of this the way it is, but if we break it down into these two parts, we can do the antiderivative of each of these. And we'll get to that part tomorrow.